Hello, everyone. We are back with another round of Turing Mock interview series. I'm Jose, tech lead at Turing, and I'm from Montreal, Canada. And at Turing, I work on hiring the best engineers by helping them with the vetting process. And just to give a bit more context about me, I have more than 17 years of experience, and my expertise lies in JavaScript. And today, I will be interviewing Pietro from the role of an experienced data science engineer. Okay, and before you ask, the question that you'll be seeing today is for YouTube purpose. Okay, if you get an interview for data science, you might get the same questions, you might get different questions, and important to freeze that these questions were selected for YouTube purpose. Okay, so let's get started. First of all, hi Pietro, how are you doing? And how is your day doing so far?
Hi, Jose. I'm fine, thanks. Day is going very well, thank you. You? How about you? All good?
Not bad at all. So I'm doing pretty well. I just came back from one little vacation, and then I'm good. So let's get started, Pedro. Let's hear a little bit from you. Okay, I would like you to let me know what is your experience. Okay, your background, your professional background, and then I'll take from there.
Okay, sure. So I am now a machine learning scientist and data scientist. I have 5 years of experience in this field. My background, my educational background actually is in physics. I did a bachelor and master's in physics. Then I did a PhD in electronic engineering and also artificial intelligence. It was a mixture of these two disciplines. And from there, I started working with like data science and machine learning, first on scientific data. Then I moved on to a research institution, the National Institute of Nuclear Physics, where I did research on the segmentation and analysis of medical images to find lesions, to classify patients, and things like that with artificial intelligence. And then I moved to Turing some months ago, where I'm doing right now NLP, natural language processing, using deep models like transformers. And I also do more like data analysis work in terms of evaluating and reporting our A/B tests.
Nice. And I would like to check your background. Okay, this is impressive. You have a professional background. And then, I've seen that you work hard to be here today. Okay, to be where you are. That's impressive. What was the I would say, one of the most interesting data science project that you have been working on?
Yes, there is a project that comes to my mind. I worked on it a couple of years ago. It was a classifier to select patients for a clinical trial. Our institution had built a machine for treatment monitoring for cancer therapy. And we had to select the correct patients for the clinical trial. This was an important task because, of course, there are very strict requirements for being selected for this kind of trials. The tumor needed to be of a certain size, only in certain places. The patient must be in specific conditions of age and the stage of the tumor and these kind of things. For this, we built something like a classifier that basically suggested the best patients based on training samples that was constituted by manually labeled patients by clinicians.
Nice. Okay, that was like amazing, pretty impressive. Okay, so let's talk about data science a little bit. Okay, how many types of biases can occur during a sampling?
Yes, there are three most important types of biases in sampling. There is the selection bias, the undercoverage bias, and the survivorship bias.
Okay, can you brief what's the difference between them?
Sure. Selection bias, well, is the most important one, and it is the bias that is introduced by the researcher when they manually or using their own experience select the sample. For example, a researcher may select a sample for a survey based on their personal friends. Maybe they will send this survey across their connections, and this, of course, will be a biased sample. It's not a correct and faithful representation of the average population, because they may be all from the same country, from the same city, same age, or things like that.
Yes.
The undercoverage bias, instead, is when the sample is too small, definitely too small for representing correctly the population. And in these cases, you have an overestimation of the most common class. So, for example, if something is mostly done by males with respect to females, then if you have a very small sample, female risk being underrepresented, even with respect to their normal percentage. And then you have the survivorship bias that happens when there are possible drops from the study. For example, typically in a clinical trial, the patient may die because of the trial didn't go so well for them. And in this case, of course, they are removed from the clinical trial and they do not participate in the study anymore. And so we have this situation. It also happens in finance when we examine past performance of funds, for example. We may be tempted to say that, oh, these funds have gone for a lot of years without great losses, but it's actually because only they are the only ones that remained alive and all the others have failed. And so this is the typical survivorship bias.
All right. And so what do you understand about bias variance trade-off?
Yes. So there is the let's say we have a model for that fits a certain amount of data, and this model can be made more or less complex with the introduction of more parameters, for example. There is a statistical proof that if we increase the complexity of the model, we are probably able to make a smaller error when we fit the data, because the model has more parameters to play with. However, there are two kinds of errors. One is the bias, that is how much on average you are off from the real value when you try to predict that value. And there is the variance. The variance is not on average, but each instance of the prediction, how much is spread out with respect to the correct value. And there is a statistical proof that as we increase the complexity of the model, we can reduce the bias down to very, very small amounts. But from a certain point onwards, we start increasing the variance. And so we lose the benefit of a more complex model.
Okay. I have a follow-up question. Okay. Is there any difference between expected value and a mean value?
Okay, no, technically there is not a very strong difference between these two terms, but usually they are used in different situations. The expected values generally refers to probability distribution. So when we talk about probabilities and things like that, we refer to expected value. Instead, the mean value is used for describing a system of random variables. And we can identify, for example, one of these variables through their mean value. And we usually say mean value, but actually saying expected value also in this case is not particularly wrong.
Cool. Okay. And what is linear regression, and what are the major drawback of the linear mode?
Okay, so linear regression is a type of model that fits data using a straight line. So using the concept of proportionality. When a variable, we have an independent variable, that is the variable that we can observe. We have a variable that we would like to predict, which we call dependent variable, usually y, and x is the independent variable. And we fit the variable y with a straight line. And we determine the coefficient of this line and the intercept of the line. of course, the linear regression has is a very simple model, and so it is very limited in the sense of the complexities that it can model. As soon as your data distribution is not linear, so it's not as a complex shape, you cannot fit it with a linear regression model. It also works best with the assumption of normality of errors, of normality distribution of variables, and they are rarely satisfied to perfection, these assumptions. And also, mostly because of the fact that it needs to fit data with a line, it cannot be used for binary outcome. So the dependent variable y cannot be a binary variable like 0 or 1. That, for example, is what happens with a clinical trial. Even there is also another issue that it's difficult to solve, especially when you have multiple independent variables, multiple x. It's difficult to solve overfitting because you don't have access to the tools to correct for overfitting in this kind of very simple models.
Okay, correct. And so, what are MSC, okay, and MST in the linear regression mode?
Yes, MSE stands for mean squared error, and is the average of the squared difference between the predicted value and the real value of any model, actually, but also, of course, in the case of the linear. The RMSE is just the root mean squared error, and so it's the squared root of what I just said.
All right, and so what is, okay, this, let's see if I can ask this question, Keith. What is a gradient and gradient descent?
Yes, so a gradient is a function that actually it's a vector that represents the derivatives of a certain function with respect to its variable. So let's say we have a variable, a function of like two variables, x and y. The gradient is the derivative of this function with respect to x and with respect to y. And so it's a vector of two elements in this case, for example. The gradient descent is like an algorithm that aims to optimize a certain objective function, we can say. So let's say we have, for example, we have defined our problem in terms of the maximization of a certain function. Let's say, for example, for a company, the ideal objective function is the company revenue, of course, with other caveats like respecting the law and things like that. But we can say that if we manage to calculate the gradient of the objective function with respect to all its variables, we can follow the gradient, which is a vector, in the direction of the steepest ascent or descent in case we want to minimize to minimize the function, or ascent in case we want to maximize the function, so that we can follow the quickest path to the optimal point of the function.
Cool. All right, so that was an impressive answer. And before we move to our next question, I just would like to call upon our developers fellow here. So Turing provides a long-term partnership with you, okay? So if you are a senior developer who has 3+ years of experience and are confident in your tech stack, you can apply for jobs at Turing, okay? And then once you pass in the vetting process, you get a job and work remotely for Turing for a long term, okay? And another thing that I would like to add here is, if you are enjoying this video or any other videos at Turing, please hit the like button and subscribe to our channel, okay, for to be close to Turing, because I'm pretty much sure that you will get a job if you be close. Even if you don't pass in the first time, Turing won't give up you, okay? You keep sending you job opportunities, and I'm pretty much sure if you learn a lot, improve your skills, you get a job, okay? Never give up, and give me a thumbs up for this video if you enjoy this content or any other content. Comment in the section below what kind of videos you would like to see in the upcoming videos. Subscribe to our channel, and that's it. So going back to our interview, Pietro, so how are the time series problems from the other regression problems?
Yes, so they are different because of the different nature of the data. In time series problems, you have data that varies with time, that makes sense to be analyzed with time. This can be a typical example is weather forecasting, or even types of revenue forecasting for certain businesses that have very seasonal periods. For example, it would not make sense to analyze the revenue of a company that, I don't know, works in the field, in the tourism field, without examining also the seasons. Probably, I don't know, a hotel on the beach will have more tourists in the summer, and so this will have to be taken into account of when analyzing their data.
Yes.
Yes, of course, this is not the case for any kind of data that has a relation with time. Sometimes the relationship with time is irrelevant for the analysis, but it becomes very important when we can identify patterns, either in a local form. So, for example, we can say that the data are very correlated when they are very close in time. This is a typical example of weather forecasting. The time today, the weather today will give you a good approximation of the weather tomorrow, at least in terms of temperature. Maybe tomorrow will rain, but the temperature will not change dramatically. Yeah. And so this is the largest difference. And of course, there is also the theme of seasonality, as I said before, also in weather forecasting is very important.
Yeah, in weather forecasts, they are saying that we can predict the next 14 days, but more close to the real weather in that time. But for a long period, they cannot be like that precise, right? So what are supported vectors in SVM or supported vector machine?
Yes, the support vectors in this kind of model identify the data points that can be also represented by vectors that are nearest to the hyperplane of best separation between the two classes. SVM is a binary classification model in which it tries to separate two classes with a hyperplane, so a plane in 3D space. And we call it support vectors because they support the hyperplane, which means that they are inside the hyperplane. So that's the reason.
Okay. My next question is, what are autoencoders?
Yes. So autoencoders are a machine learning model that tries to replicate the input on their output. So this is a typical application of compression algorithms. You try to you get an input, you compress it with we call it the encoder part of the autoencoder. And you compress it into what we call a latent representation, which is a compressed form of the input. And then from there, you have the decoder that tries to, from the latent representation, to extract the input as it was originally. Of course, in case of lossy, we call it lossy autoencoders, we lose some quality of the representation. For example, it can be an image compression algorithm that degrades it a little bit, but compresses the image a lot.
Okay, and what are, in your understanding, the best practices to reduce the errors during this encoder from the input to the output?
Yes, so very important is the loss function. The loss function is the function that you try to optimize when you train the model. You can create a very generic loss function like MSC, that we talked about before, mean squared error between the input and the output. And this will, of course, tend to have the output equal to the input. But very often, we are not really interested in all the characteristics of the input to be maintained in the reconstructed output. For example, in image, when we use them on images, we may not care if certain colors are slightly changed, but what we really care is that the image itself is preserved. For example, this can be used if you don't really care about the quality of the image, just of the representation, you can create a new loss function that takes this into account. Other strategies, I use variational autoencoders, which is a particular type of autoencoders that try to use specific loss functions that learn from the distribution of the input, like they learn the mean and the variance, and then try to apply it to construct a better output.
Cool, really cool. And my next question, there's no right or wrong answer. Okay, it's more about you. How do you approach solve any data analytics based project?
Yes. So the first thing, of course, is to understand the problem. Try to get as much context and input from the relevant stakeholders. Understand where the data are located. Understand the data quality, which means that to see whether these data are reliable, whether they are complete, whether you have a very large coverage of the phenomenon that you want to study or not, and whether there are missing values, of course. And once you have explored the data, you can start the data cleaning operation. That means basically identifying missing values and trying to either impute them or generate a strategy that can deal with missing values. For example, there are models that do this, like gradient boosted decision trees that work very well with missing values. And then, of course, you have to, depending on the request that was made, either prepare a report or fit a model. On this, I would always start from low complexity models because of the bias variance problem that we discussed before. Very complex models tend to overfit the data and have a very high variance in their predictions. So we always start with simple models, and then we go to more complex ones as the simple model fails. But very often, even simple models can give a pretty good answer to the problem.
Yes. Then, go ahead. Sorry.
Yes. And then there is, of course, implementation, put into production, if it's a model that can be used for production, and A/B tests and validation of them.
Cool. And I'm glad you mentioned missing values. Okay. During in your analysis, how do you treat the missing values?
Yes, of course. So this depends a lot on the task and on the type of variable that has missing values. First of all, we need to identify a pattern, whether there is a pattern. Sometimes, for example, you can, let's say you are analyzing, I don't know, prices for houses. You see that houses sold in a certain town, they have all missing values in terms of prices. So probably this means that whatever collected the data there didn't do a good job. And so here imputation is a bit dangerous because these are not randomly missing values. They all miss for a specific reason and in a certain place. When there is no pattern, instead, you can try to substitute missing values with proxies, like the mean of the values that are there, instead the median, or for continuous value. For instead categorical variables, you can try to use a category. Let's say you have a variable that can be yes, no, or missing. Right? In this case, if you encode it as a 3-valued variable instead of yes, no, and missing, you can say A, B, C, and C is missing. Then the model, if you have a good model, the model will learn that whenever you put C, that means missing, and you can go on with the analysis.
Thank you, Pietro. That was my last question. Okay, it was a really nice speak with you today, and that's it.
Thanks, Jose. It was very nice to be here. Nice opportunity.
My pleasure. And to everybody else, thank you for tuning into this mock interview series. I hope you all enjoyed this video as much as I did. And we will be back very soon with another episode for a mock interview covering different text and language. And if you are looking for some particular text or language, drop your message in the comment section below. You can let me know, and then we're going to record this video for you. Okay, don't forget to subscribe to our channel and give us the big fat thumbs up if you enjoy this video or any other video at Turing. Till then, I hope you all have a great day and see you all in the next video.